Okay, so next we will begin to explore the concept of the extrema of a poset. So let the set X together with some relation R be a poset. An element X in the set X is called a minimal element. If there does not exist a distinct element Y in the set X such that Y is related to X. The element X is called the least element and this is denoted X is equal to the min of X if for every element Y in the set X we have that X is related to Y. So notice that the least element if it exists is also a minimal element. So let's look at an example. Let the set A be the set containing the integers 2, 4, 5, 10, 12, 20, and 25. Then the poset formed from the set A together with a relation less than or equal to has one minimal element, which is also the least element, namely the integer 2, and the poset formed from the set A together with the relation divides has two minimal elements, namely the integers 2 and 5, but no least element. So proof. For the relation, or rather for the poset, consisting of set A with the relation less than or equal to, we have that 2 is less than or equal to 4, which is less than or equal to 5, which is less than or equal to 10, which is less than or equal to 12, which is less than or equal to 20, which is less than or equal to 25. So here we have one long chain. So notice that there does not exist an element X which is distinct from the number 2 in the set A such that X is less than or equal to 2. And so the number 2 is a minimal element. Further, for every element Y in the set A, we have that 2 is less than or equal to Y, and so the number 2 is the least element. So for the poset formed from the set A together with the relation divides, we have that 2 divides 4, which in turn divides 12. 2 divides 10, which in turn divides 20. 5 divides 10, which in turn divides 20. And finally, 5 divides 25. And so we can construct a diagram that shows this relation. The integer 2 divides 4, which in turn divides 12. The integer 2 divides 10, which in turn divides 20. The integer 5 divides 10, which in turn divides 20. And finally, the integer 5 divides the integer 25. Now, this diagram is an example of what's called a Hasse diagram, and it is named in honor of the German number theorist Helmut Hasse. So notice that there does not exist an element x which is distinct from the element 2 in the set A, such that x divides 2, and there does not exist an element y which is distinct from the number 5 in the set A, such that y divides 5. And so the numbers 2 and 5 are minimal elements. Now notice that there does not exist a single element x in the set A, such that for every element y in the set A, x divides y. And so there does not exist a least element. So next, as a lemma, let x together with some relation r be a poset. Then the least element if it exists is unique. So proof. Suppose that x and y are both least elements. Then, as x is a least element, it is also a minimal element. And so there does not exist a distinct element y such that y is related to x. And hence, if y is related to x, then necessarily y is equal to x. So as y is a least element, y is related to x for any x in the poset, and so we can conclude that y is equal to x. And so if the least element exists, then it is unique for a given poset. So once again, let the set x together with some relation r be a poset. An element x in the set x is called a maximal element if there does not exist a distinct element y in the set X such that X is related to Y. The element X is called the greatest element and this is denoted X equals the max of the set X if for every element Y in the set X we have that Y is related to X. So notice that the greatest element if it exists is also a maximal element. So as an exercise, let A be the set containing the integers 2, 4, 5, 10, 12, 20, and 25. For the poset, consisting of the set A together with the relation less than or equal to, and the poset consisting of the set A together with the relation divides, determine the maximal elements and the greatest elements if they exist. And as a second exercise, let X together with the relation R be a poset. Prove that the greatest element if it exists is unique. Okay, so new definition. Let R be a total ordering on a set X such that the relation R is irreflexive and transitive. Then the relation R is a simple ordering on the set X, and the set X together with this relation R is called a simply ordered set. Now I need to point out that a simple ordering is sometimes called a strict partial ordering Now I will not be following this naming convention, since for a simply ordered set the relation is irreflexive, while for a partially ordered set the relation is reflexive, and these are mutually exclusive properties. I also believe that it is more beneficial and more convenient to have a separate term for a separate structure. So as an example, we will show that the set of integers together with the relation less than is a simply ordered set. So proof. For every distinct pair of integers, a and b, either a is less than b or b is less than a, and so the relation less than is a total ordering on the set of integers. Now for every given integer a is not less than itself, and so the relation less than is irreflexive. Now let a, b, and c be three integers, and suppose that a is less than b and b is less than c. Then a is less than b, which in turn is less than c, and so a is less than c, and hence the relation less than is transitive. And so the relation less than is a total ordering on the set of integers that is irreflexive and transitive, and therefore the set of integers together with the relation less than is a simply ordered set. So next, as a lemma, we will prove what is known as the trichotomy law. Let the set x together with the relation less than be a simply ordered set. Then, for every pair of elements, x and y, in the set x, exactly one of the following is true. X is less than y, x is equal to y, or x is greater than y. So proof. As the set x together with the relation less than is a simply ordered set, the relation less than is a total ordering on the set x. And so for every pair of distinct elements, x and y, in the set x, either x is less than y or y is less than x. That is, either x is less than y or x is greater than y. And so for every pair of not necessarily distinct elements, x and y, x is less than y, or x is equal to y, or x is greater than y. And these are pairwise mutually exclusive, and so exactly one of them is true.